the first part of this video, we will solve this problem, square root of this, the calculation problem. In part 2, we will solve first problem of USACO silver part, first contest, December 2022, and we will consider ideas that are useful also for 2023, 2024, and so on. And in part 3, I leave homework. Okay, let's start. And if you want to learn more ideas and important ideas that are useful in Olympiad math exam, or for useful for Olympiad in informatics like USACO, Math Olympiad like USAMO or AMI, AMC, if you want to learn important ideas, feel free to send message to my WhatsApp number in the description. Okay, we are given this square root. What's the relationship between numbers? 12, 13, and 25. 25 is 12 plus 13. We can consider 12 as A and B as 13. So 25, when we are working with numbers, one useful way is to use changing variable. Okay, so when we consider A equals 12, B equals 13, 25 is what? Is A plus B. So suppose here it is inside, for example, T over 2. So T is this part. So we can say T is what? In terms of A and B, 12 to the 4 is A to the 4 plus. So we've considered numerator as T, okay? Square root of T over 2. So T is 12 to the 4, A to the 4, 13 to the 4, B to the 4, plus 25 to the 4, A plus B to the 4. Okay, for this one, we should apply binomial expansion or binomial theorem. A plus B to the 4, we can write it as 4 brackets. A plus B, A plus B, A plus B, A plus B. And then it will be what? You say, okay. The terms, one term can be A to the 4, so we select 4, choose 4 from all brackets A. If we choose 3A, A cubed, then the last one B. Plus 4, choose 2, A squared, B squared. Plus, if we select 1, also we can say here 4 choose 0, A to the 4, because when we select 4 A's, it means that we select no B. So A, B cubed, plus 4 choose 0, B to the 4. Okay. So if we apply this, it will be what? A to the 4, plus B to the 4, plus here, 4 choose 4, A to the 4, and as homework 1, try to write A to the B, A plus B to the N is what? Comment your answers right below this video. Here it will be what? A to the 4. 4 choose 4 is 1. 4 choose 3 is 4 choose 1 is 4. Plus 4A cubed B. Plus 4 choose 2, N choose 2. When you want to calculate, for example, 4 choose 2 or N choose 2, N choose 1 is always N. N choose 0, also you can say it is equal to N choose N minus 1. N choose 0 equals N choose N equals 1. For example, N choose 2 is N times N minus 1 over 2. Okay, so by applying this, so 4 choose 4 by applying this one, 4 choose 3 by applying this one, 4 choose 2 by applying this one, 4 times 3, 12 over 2, 6. And they have a formula, all of them. You say, for example, if N choose 3, N minus 1, N minus 2, 3 terms in numerator over 3 factorial. And also, for other terms, you can do same thing. If you had question or wanted to learn more ideas, feel free to send message to my WhatsApp number in the description. Now, next one. 4 choose 1 is 4. 4 times AB cubed plus 4 choose 0 is 1. B to the 4. Now, in this part, we will see we have 2A to the 4 plus 2B to the 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed. It is t. Now if you divide t by 2, then let's see, it will be what? T over 2 will be a to the 4. You divide, let's write in decreasing order of powers of a. So it will be a to the 4. If we divide by 2, 2a cubed b plus, so this one. Next one, 3a squared b squared plus 2ab cubed and plus b to the 4. Okay. For next part, I want to write this as something squared. And for this part, let me tell you, identity 4a plus b plus c squared is what? You can write it twice and it will be a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc. 2ab plus 2ac plus 2bc. Apply this identity 4 and see this part is what squared. Try first on your own. Pause the video and try. Because we have a to the 4, we write a squared. Because we have b to the 4, we write b squared. And as you can see, for example, we have 2a cubed b. Something like this. 2 times this one times what will be a cubed b, ab. Now let's check. Is it correct? A to the 4, b to the 4, a squared, b squared here, but it's 3. Because 2 times this again will be a squared, b squared. Plus a squared, b squared, 3a squared, b squared. 2 times this one times this one, 2 times a cubed b, 2 times this one times this one, 2ab cubed. Okay? So it will be this. Now, if you take square roots, square root of t over 2 is a squared plus b squared plus ab. Now a is what? A is 12, b is 13. A is 12, b is 13. So the answer will be what? 12 squared plus 13 squared plus 12 times 13. 12 squared is 144. 13 squared is 169. 12 times this, you can write 13 or imagine is as 12 plus 1. So 12 squared again, 144 plus 12. Now, if you add all these numbers, 2 plus 4, 6 plus 9, 15 plus 4, 9. 19. We have 1. 1 plus 1, 2 plus 4, 6 plus 6, 12 plus 4, 16. We have 1. 1 plus 1, 2, 3, 4. So the answer is 469. Now let's again as I said before, if you want to learn more ideas, feel free to send message my WhatsApp number in the description. Now let's try this problem from USACO silver part. Read this problem, pause the video and read it first on your own. If we consider this problem as a graph, we have n vertices, n minus 1 rows, and it says what? It is possible to get from any barn to any other barn via some sequence of roads. Means we have tree. Tree is what? Is connected a cyclic graph like this one. For example, this. And in all of them, number of edges. If number of vertices equal to n, then number of edges equal to n minus 1. Okay? So we have 3, and it says what? Let's consider example to understand problem better. Here, for the first one is n, means we have 4 vertices. And edges are these lines, I will explain. That second line is what? So we know 1 to 2, these 3 lines are our edges. 1 is connected to 2. 2 is connected to 3. 2 is connected to 4. Okay. Now it says what? Let's consider second. We have 4 bars. And these 4 numbers show that how many hay bales each of them has. So for example, first one has 2 hay bales. First one is this 2 hay bales. This one hay bale, and third one has 4 hay bales, and third one and fourth one has 5 hay bales. And we want to move, for example, from some of them to the other. At the end, we want to reach 4 equal hay bales. Okay, so let's see, we should reach to what number? Again, the graph won't change. Now, if we want to reach equal hay bales, what's the sum of hay bales here? 1 plus 2 plus 4 plus 5. It is what? 9, 11, 12. Now, if we want to distribute equal hay bales, it will be 12 over 4 because we have 4 vertices or 4 barns. It will be 3. So all of them should reach 3. Okay, now we can say because they want to reach 3, these two has 1 less than 3, this one has 2 less than 3, 4 has 2 less than 1 less than 3, 1 more than 3, and 5 has 2 more than 3. Now let's see how we can move. It says with minimum number, look here, out with the minimum possible number of out orders, followed a sequence of order of that length. Okay, one per line. Here we have one smaller than the thing we want. We want to reach all of them to 0, okay? I've considered each of them minus 3, so we should reach 0. For this one, because it is 1 less than this, we need 1. Or something should reach this one, and at the end we tell you 1 is okay, 1 is the best choice. So here, because we have 1 more, we should have direction from here to here. Because it has 2 more, we should have direction from here to here. So we should have at least 3 movements. And if we consider 1 here to satisfy this, 1 here to satisfy this, to reach 0 for this one, 0, 2 for this, 0, 0, 0, and 1 will be cancelled, 2, negative 2 will be 0, all of them will be 0. So you say what? 3 movements, and the order is important. Why? Because, for example, let's consider here 1, 1, 2. Here, because it has 5 to move 2. Here it has 4 and you can move 1. But if we wanted, for example, to move 6 here, it was not possible. I would explain in a bit complicated cases that why the order is important. Here it's not important in this case. So it says what? 3 movements. 3 to 2 to 1. 3 to 2, 1. We should move 1 hay bale from 3 to 2. And 2 hay bales from barn 4 to barn 2. This one, and 1 hay bale from vertex 2 to vertex 1. Okay, so it is explanation of this. Now let's see how we can solve this problem. Let's consider a larger example. For example, like this one. And we consider like this, the first one as root, 1 vertex as root. And this one, 2, 1, 1, 2, 3. Let's do something. Here we can consider this fourth, and we can consider this, and this one, and this one. Okay, so here suppose these are our vertices, and for example, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. And suppose number of hay bales equal to, for example, this one 1, this one 10, this one 1, this one 0, this one, let's consider 8, this one 3, this one 2, 4, 1, 12, 3. Okay, for example, this one 15, this one 2. Okay, and consider, for example, this one as 10, and 9, and 2, and for example 2. Okay. Now we want to see the algorithm is what. At first, we should see they want to reach what number of hay bales, because number of hay bales should be equal for all of them. So if we add 1 plus 10, 11, plus 2, 13, plus 4, 17, 18, 19, 29, 31, 33, 36, 38, 46, 56, 61, 71, 80, 82, 85. Okay. I've considered numbers to reach 85 because the problem says it should be multiple of number of vertices. Means it says it's possible to reach the case that all of them be equal. Because we have 17 vertices, you say sum of them is 85. If we divide by 17, so all of them should reach 5. Okay. And now I subtract all of them. I consider all of them minus 5. Okay. And then I draw new tree. Let's draw new tree and consider, let me open the page. So let me write here, it will be what? Negative 3. And this one, 2 minus 5, negative 3. 10 minus 5 is 5. 2 minus 5, negative 3. 9 minus 5 is 4. 3 minus 5 is negative 2. 15 minus 5 is 10. 3 minus 5 is negative 2. 8 minus 5 is 3. 1 minus 5 is negative 4. 4 minus 5, negative 1. 12 minus 5, 7. 2 minus 5, negative 3. 1 minus 5, negative 4. 10 minus 5 is 5. 1 minus 5 is negative 4. And 0 minus 5, negative 5. Okay. Now we can erase other numbers. Now it's easier to work with. We want to reach 0. Okay. And this one, this one, this one, this. Okay. So let's add all these numbers. For this one is 1 minus 2. For 11 it was negative 4. Let me write it near to that number. Negative 4 here, negative 5. Here, negative 3. Okay. Negative 7 plus 5, negative 2. Negative 2, negative 1, negative 3. Negative 4, negative 7. But was and 7, 0. This one, negative 9, negative 12, negative 14. Negative 11, negative 14, negative 4, negative 6, negative 1, and 3, and negative 3, 0. Okay, we want to reach 0 for all of them. So here we can obviously find that when it is negative 4, at first we should do something for these things. Okay, so you need 4 from this part. And let me tell you why order is important. Here look, it's 2, and we know at the end we should move 4. So if in first step you want to move 4 hay bales from this vertex to this vertex, we have problem because it has 2. And the problem says when you move something, we should have that number instead. This one, 4 should be less than or equal to, which is not. But let me tell you, at first we determine each edge is what, and then I will tell you the order how we can do something, how we can, for example, find a good order that satisfies all the conditions of the problem. So here we need 4. This one will be okay. For this 5, we need 5 from here to here. Now this vertex will be okay. So 5 inside, 4 outside, so it will be 1. Net value will be 1 inside. 1 inside, it is negative 3, negative 3 plus 1, negative 2, so it needs 2 from here, okay, from the parent. And now this one, you should move 2 here, it's negative 1, so negative 3 net value, so we need 3 from this point. Now let's consider for other leaves. First, negative 4, it needs 4, now this one will be okay, so this one also okay, this one okay. So this one 5, it needs 5. So this one will be okay. 5, 4, 9 outside, it has 7 net value, will be negative 2, so we need 2. this one will be okay. Now this one, 3 more, so 3 may be moved, this part, and then 3 plus minus 2 is 1. So it moves 1 here. This one, it will be 2. This one, okay, this one, okay, this one, okay. And now, let's also consider this part 2, 5, 3, 5 goes outside, -4. Net value -9, so it needs 9. Now for this part. 2, it's -2, sorry, so we should move 2 to vertex 13. Now this one will be okay. For this one, 4 here, 3 here. These two things will be okay. 4 inside, 3 outside. So net value 1 inside plus 5, 6. So we should move 6. Now this will be okay. We should reach 0 for each vertex. Now 2 outside, 10. Net value is 8. So 8 here, 8 plus 6, 14. 14 minus 3, 11. So 11 here. And as you can see, this one, okay, all these vertices will be okay. Now 11 and 1 inside, 12. 9 outside, so 3 inside, minus 3, 0. This one also will be okay. We can prove if all vertices be okay, then this one will be okay. Now, I want to, so you can apply this by using DFS, okay? We can find this easily. How? Consider these numbers that I found for each of them. I will explain how to write, or let me explain for you first how you can find these numbers. Now we've created a directed graph, okay? I will tell you how to reach this directed graph. The code is what? And then after that, we should find a good order of movements, okay? If we want to type the code, at first we get all these numbers, then we calculate 5, and then we subtract 5 from all of them, and then we reach these orange numbers. Then we want to create this directed graph. How we can do that? You should define a function, DFS, and it gets x and parent of x. So when you want to call it for first time, for example, you call DFS of if it is 0 base, or let's consider 1 base here, DFS of 1, and for example -1000. Why? Because 1 has no parent if the root is 1. And then you call this one. Now DFS x and parallel x is what? Here for a number like 2. It calculates all these things. It has some children like this. And then it understands what, for example, 3, we should move for this vertex 2. Let me explain for vertex 2. For vertex 2, if we consider these things, we understand that we should move 3 and 2 to this one. So we say 3 plus 2, 5. Minus 4 is what? 3 goes minus 3, minus 2, because we should move hay bales from here to these parts. And this one is what? -4. So it will be -9. So then for a vertex, like here, x, and for example, this one is parent of x, we will see, okay, we have some movements like this for each of them. We reach some values. Net value for each of them. For example, look, net value for this one is -4. 5 for this one is what? -3. -4 plus 5. Okay? So 5 minus 4, 1. 1 minus 3, it will be negative. 5 minus 4 is 1. 1 minus 3 is -2. So it's -2. So we should find these black numbers. Okay? So we call these black numbers, for example, net value. So here you consider, okay, all childs you consider for I from is child of x. You consider what? You say sum 0, for example, sum plus equal to what? DFS of I and, for example, this one, I, and parent of that is what is x. Okay, now we get all these things as sum. Then this one has a number, so for example, we call this orange number as b. Okay, so our b's are what? For first one is -3, for 2 is -4, and so on. Then we say sum plus equal. Plus equal, I mean sum equals sum plus what? B of x. Okay. Now it is the number that we need. So you say what here? Net value of this part. Net value of x is sum. And then you return sum. Okay, in first part now we can find these values. Okay, now I want to draw this directed graph. So before finishing this one, I should consider two things. If the net value of this is positive, we should move to parent. If it is negative, we should get from parent. Okay, so you say this part. If sum is positive, then we should add this edge, x2. Parent of x, and the value is what this net value of x. If sum is 0, we don't need to add any edge. If sum is negative, sum means net value of x. Then we need this value from parent of x to this minus sum, or minus net value of x. Then it will be positive. So we should get from here. Let me explain the figure. For example, for this one, when -2 is negative, so you should get from parent of x to this one -2, which is 2. When it is negative, from parent of x to x. And sometimes it's positive, like this one, this 5. It's positive, so you should move this one to this one. So these things are related to our directed graph. Okay, now we've created this directed graph. Okay, now let's see what should we do. Let me copy this one and erase all the numbers that we don't need. Okay, so -3. Let me erase these numbers. We should move. And this part, okay. This part. 9, -4, this one. Let's erase this one. This one, okay. Now we should move these values like this. Okay. So as you can see, the order is important. Now you can consider all edges. You can add these edges, and your answer is that. Okay. So you can say each part that you add an edge, number of edges, you say, okay, edge is edge plus 1. Each of these cases, okay, here or here. Then, so our answer, you print or see out number of edges first. It means number of movements. Now for this part, I know that the order is important. But for example, for this one, we know it doesn't have any in degree. In degree means nothing comes to this vertex. So we know that we can start from this part. So this graph is a DAG. DAG is what? It's a directed graph without any cycle. Or we can say directed acyclic graph. And it means what? It means that we don't have a directed cycle like this. There is no cycle like this, and because it is a tree, we know the edges in general. In main graph, we don't have any cycles, so in directed graph also we don't have any cycle, and it is not necessarily connected. Okay, so here there is a theorem that when you have something like this, you can apply topological sort. It is what? It means that you can consider vertices in an order that all directions are from left to right. Okay, we don't have any direction like this. And how we can prove this? Let me tell you the proof of this, that there exists an order that all directions are from left to right. At first, I want to prove there exists a vertex, for example, A, such that in degree of A, in degree means, for example, when we have this, it is this. In degree of this vertex is 2, out degree is 1. Okay, so it means the edges that are directed inside this vertex in degree, outside this vertex will be out degree. That in degree of A is 0. Why I can prove this, that there exists a vertex that in degree, if in degree is 0, I place that one first vertex in our order, and then I continue like this. The proof is what? Let's prove it by applying contradictions. Suppose we don't have anything like that. So if we consider a vertex, it has at least one in degree. Then this one at least 1 degree, 1 degree. We cannot select infinitely many vertices because there are finite number of vertices. So then for in degree of this, we should select one vertex that we've seen before. So like this, then we have this directed cycle, which is contradiction. Now by applying this, you consider, for example, A as first vertex, okay? Then we remove A. A is connected to some of them, and we know all edges from A are from A to some other vertices, and we remove A. Then the rest of the graph again is a DAG, okay? Because by removing a vertex, you cannot have a directed cycle, because before that we didn't have, so after that we cannot have. Again, you do the same thing. There exists a vertex that in degree is 0, like B, then you place B here, and you continue like this. Okay, so we proved this, but how can we type the code? The code is like this one. Let me apply on this graph, then you will understand the algorithm is what, and you can apply this. Okay. So for this one, you say, okay, let's consider an array. Okay. And then you say which vertices have degree 0. 17, you add all of them to this. 17 we apply degree in degree 0, in degree 0, in degree 0, not this one, this one, this one. You check first. By 1, 4, you can find all of them. 7, and then 13 in degree 0. You can also add 8 in degree 0, in degree 14. Okay. Now I've applied these things, okay? So then I remove 17, I remove 17, and I check. When I remove 17, I check. Is in degree of the vertex that is connected is 0 or not? 10. The in degree is not 0. Now let's erase 7. We erase 7, and after removing 7, we see, okay, 3 in degree of 3 is 0, so we add 3. Okay, now our pointer was on 7. Okay, we've checked 7, now let's move it. 8. Let's remove 8. Now we check all the edges from 8 to other vertices. Now 13 is 0, so you add this. So you can consider this one head pointer, tail pointer. We add 13. And for 4, it's the in degree is not 0, okay? So let's check next one. Our head 14. So 14 is connected to 9. So we add 9 and we remove 14. We add 9. Okay. And 9, the integer is not 0 too. Oh, sorry. 9, the integer is 0, so we add. Like this. Okay, so let's do something like this. We are in 14. Now, let's check next one. We've added this and this. So let's check 3. For 3, here, we add, we remove 3 and we check in degree of this is 0. No, it's not 0. So let's erase 3. Now we are in 3. 13 after that. Okay, we are in 13. It doesn't have anything after 3. Okay, so let's consider 9. We are in 9. Okay, so 9 is connected. When you remove 9, 9 is connected to these two things. When you remove 9, in degree of these two things will be 0, so we add 15 and 4. Okay, so next we check 15 and we remove 15. Next we check 4. And when we are checking 4, we remove 4 and in degree of 1 will be 0. Okay, we add 1. Then we are in 1. We remove 1 and we will see in degree of 2 will be 0. So we add 2. Now we are in 2. We remove 2 and then we will see in degree of 5 and 6 are 0. Now we are in 5. We check 2 and then 5. For 5 we remove 5. In degree of 10 will be 0. So 10. Then we are in 10. We are in 6. And if we remove 6, we can add 11, 12. Okay, now let's check 10. When we remove 10, then 16 will be 0. So you add 16. And then 11, then you check all of them and you do this. Let's check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We've added all of them like this. And if you see all directions, it is our main graph. All directions are from left to right. For example, look this word, this edge. 7 to 3. 7 to 3. This one. 8 to 4. 8 to 4. This one. All edges are from left to right. So, when you want to type these values, you start from 17. You say, okay, 17 is connected to which vertices? So 17 to 10. 17 to 10. And we know that we don't have anything that come inside 17, so we can apply this 5. It has enough because we don't have any in degree to 17. Okay, so you apply 70 to 10, this one, and then this one will be okay. Okay, or you can say this one, okay. And then after that 17 finished, let's check 7. For 7, we apply these 3 and it will be okay. Then for 8, you apply this one and this one. 8 to 4, 8 to 13, this one okay, this one okay. For 8. After that for 14, you apply this one, it will be okay. For 3, 3 is 1 to 3, 1 to this part, it will be okay, and so on. You can continue like this. And 13, it will be what? 11, 12, 13, we've checked. We don't have anything that goes 13 from 13 to for example, other vertices. This one, okay, 9, from 9 to 4 and 15, these two things, it will be okay. From 15, here we don't need anything. For 4, 1, 2, 3, 4. As you can see, when you reach a vertex, we have only edges that are from that vertex. For example, 4 to others. In degree is 0 because we've erased all things that were related to in degree. So 4 to this one, you remove. Then for 1, you apply this one. For 2, you apply this one. You type as output. For 5, this vertex, you print this one. For 6, you print these two edges. For 10, you print this edge. For 11, 17 was here at the beginning. We consider then for 11, for 12, and for 16. We've applied all of them and you type this. Okay, so how many ideas did we have in the beginning? Idea 1, 2, 3, and 4. So this one, how we applied DFS was idea 5. How to create this directed graph, idea 6. How that is what idea 7, topological sort idea 8, and the proof idea 9, and how we apply the code, it will be idea 10. Okay? Now let me tell you a homework. This problem is related to recursive sequence and is good for also USACO because dynamic programming, USACO, and also useful for USAMO because related to recursive sequence. And you can do this one as homework. It is IMO 2011. These types of problems, when you solve it, is also good because when you type the code, it is for dynamic programming. And maybe in dynamic programming, it says, okay, for example, the answer is what for N, for general N. And this thing, if you want to learn in recursive sequence and dynamic programming, there are some ideas. If you want to learn those ideas, feel free to send message my WhatsApp number in the description. Okay, we can work on WhatsApp number in the description. We can work on important ideas, USACO, USAMO, bronze part, silver part, gold part, and other parts. If you want to prepare for that or any other math exams, as I said before, you can send message to my WhatsApp number. Okay, have a great day. Don't forget to subscribe, turn on the bell, and like the video. Thanks. Bye.